comparison of Valence bond theory and molecular orbital theory. Is it visible? Yes. Okay, first points of resemblance means points of similarity. We compare them. First we write the point which are similar in both the theories. First point, similarity. First point is both theories both the theories are based on approximations. Both the theories are based on approximations. Okay, because valence bond theory takes into account the valence electrons in nucleus and electron attraction, electron repulsion, nucleus repulsion, and molecular orbital theory deals with that when atoms combine, molecule is formed, then atomic orbitals are transformed into molecular orbitals, bonding and anti-bonding. And in both the theories, in first case atomic orbitals overlap. In molecular orbital theory, when these atomic orbitals overlap, we get molecular orbitals, and this orbital overlap is necessary for the bond formation. According to both the theories, orbital overlap is necessary for chemical bond formation. Orbital overlap is necessary in both the cases. Those orbitals which overlap with each other, they should have almost similar energy in both the theories. Okay, so the overlapping atomic orbitals should have nearly same energy, either equal or comparable. According to valence bond theory, when bond is formed, then what happened? There is electron density between the nuclei. Okay, and even in molecular orbital theory, when atoms combine and bonding molecular orbital is formed, and which is in favor of chemical bond formation, then there is an increase in electron density between the bonded nuclei. Right? So both theories predict that concentration of electron density both theories predict that there is increase in concentration of electron density between the nuclei, between the bonded nuclei. Okay, so according to both the theories, orbital overlap is necessary. According to both the theories, electron density between the nuclei increases. According to both the theories are just an approximation. Both the theories predict both the theories predict the directional nature of bonds. Directional nature of bonds, because both are in accordance with covalent bond formation. According to both the theories, helium-2 or neon-2 or any novel gases N2, or you can write helium-2, neon-2 does not exist. But helium-2 is well known to us, so write helium-2 or any novel gas compounds. Helium-2 does not exist according to both the theories. Very good, because according to Valence Bond Theory, repulsions are dominating over attractions, and according to MOT, bond order between the helium-helium atom is 0. Rules for filling electrons, that is Aufbau principle, Pauli's exclusion principle, and Hund's rule are applicable according to both the theories. So these are points of resemblance between Valence Bond Theory and Molecular Orbital Theory. First, both are approximations. Both tells us about the orbital overlap concept. Okay, both tells us about that electron density between the nuclei increases. Then both tells us about the directional nature of the bond, or both theories tells us about that helium-2 does not exist, or electron filling takes place according to the rules, that is Pauli's, Aufbau and Hund's. So these are the similarities or point of resemblance between Valence Bond Theory and Molecular Orbital Theory. Now points of differences. So one side write Valence Bond Theory, on the other side write Molecular Orbital Theory. So first is, according to Valence Bond Theory, electrons are localized. Electrons are localized as in case of isolated atoms. Means electrons are not delocalized, but according to MOT, electrons are delocalized because when atomic orbitals combine, because molecular orbitals are polycentric. They are around the space where there is a combination of nuclei. Okay, that space is considered. But in this case, the space around the nuclei is considered. Okay. Second point. Here electrons are localized, as in case of isolated atoms. Here electrons are delocalized because molecular orbitals are polycentric. Yes, very good here, Ralan. So in this case, the atomic orbitals, in this case, atomic orbitals do not retain their identity, individual identity. They are converted into molecular orbitals and they lose their own identity. But in case of valence bond theory, atomic orbitals of combining atoms retain their individual identity. To a large extent. But in case of MOT, atomic orbitals of combining atoms, atomic orbitals of combining atoms lose their identity and molecular orbitals are formed. Right? Then third point. Wow, Mansi, very good, beta. So, according to VBT, when bond is formed, there is an increase in electron density between the nuclei. But according to MOT, when atomic orbitals combine, either bonding molecular orbital is formed or anti-bonding. So, in bonding, electron density between the nuclei increases. In anti-bonding, electron density between the nuclei decreases. So here increase or decrease in electron density between the nuclei, but here only increase. Right? So the valence bond theory takes into account only increase in electron density between the bonded nuclei or combining nuclei, right? But here, according to MOT, in MOT there is increase or decrease in electron density between the bonded nuclei, right? Okay, yes. In this case, valence bond theory, tell me what number of covalent bonds. how do we calculate number of covalent bonds in valence bond theory and MOT? Yes, in MOT, bond order is calculated by, yes, write the formula used. If you have watched the video, you should know. Bond order is equal to, according to molecular orbital theory, bond order is equal to yes, follow. It is bonding, number of bonding electrons minus anti-bonding divided by 2. Have you gone through this formula? Yes, beta, tell me. Okay, so that means number of covalent bonds in valence bond, number of covalent bonds according to VBT is equal to number of orbitals with unpaired electrons, right? Like ammonia, it has 3 unpaired electrons, so it forms 3 bonds. Oxygen has 2 unpaired electrons, so that form 2 bonds. But in this, according to MOT, number of covalent bonds, that is also called bond order, is equal to difference, half of the difference, is equal to half of the difference between bonding electrons and anti-bonding electrons, right? Half of the difference between bonding electrons and anti-bonding electrons. Done? Okay. Any other point? Okay, good. Yes, Ralam told me earlier, it does not predict the paramagnetic or diamagnetic behavior of molecules or ions, right? But MOT, it can predict the paramagnetic or diamagnetic nature of molecules. Okay? Now, sixth point. Which one is easier to apply? You know, MOT, in VBT we just see the repulsions and attractions and that's all. But in this case, we have to calculate bond electronic first we write electronic configuration, then bonding electrons, anti-bonding electrons, unpaired electrons, all that we have to see. Okay, so it is easy to apply. Right, but it is difficult to apply. And last point, resonance. Resonance has very good role to play here in VBT, but there is no role of resonance in MOT. Resonance play an important role in VBT, in this theory, but resonance has no role to play in MOT. So these are points of resemblance and differences between VBT and MOT. Question number 21 is, apart from tetrahedral geometry of methane, apart from tetrahedral geometry of methane, another possible geometry is square planar, right? With 4 hydrogen atoms at the corners of the square, with the carbon atom at the center. Explain why CH4 is not square planar. Yes. Say in tetrahedral, it is non-planar and bond angle is HCH bond angle, that is 109 degree 28 minutes, right? But in square planar, this is tetrahedral. In square planar, it is like this. And here HCH bond, that is 90 degree. So according to Vesper theory, according to valence shell electron pair repulsion theory, shared pairs are arranged in such a way, or we can say electron pairs. Here there are only shared pairs, so we write shared pairs. Shared pairs around central atom are arranged in such a way that there is, yes, we can write, yes, there is minimum repulsion, right? Minimum repulsion and maximum stability. That is the main motto of Vesper theory, that we have to arrange shared pair in such a way that there is minimum repulsion between the electron pairs, and repulsions are minimum when angle is maximum, right? So angle in tetrahedral is greater than in square planar. That's why there should be tetrahedral arrangement, so that stability is maximum for the particular arrangement. Okay. So repulsions are between shared pairs are minimum when angle between them is maximum, and that is in tetrahedral arrangement, right? That's why geometry is arrangement. Okay, so geometry of methane is tetrahedral and not square planar. Okay, so this is the 21 question. Now question number 22. Question number 22. Explain why BaH2 molecule has zero dipole moment, although the BEH bonds are polar. BAH, see, in BH2 beryllium central atom has two bond pairs and no lone pair. So geometry is linear and angle is, bond angle is 180 degree, right? And BEH bonds are polar because of electronegativity difference, between beryllium, that is 1.5, and hydrogen, that is 2.1, right? So you know, direction of polarity or dipole moment is towards more electronegative, but polarity due to one BEH bond is exactly cancelled by polarity due to other BEH bond, right? That's why BEH2 has zero, can I write here? Yes, has zero dipole moment and is non-polar molecule. Say, molecule has polar bonds. Molecule has individual polar bonds, but net polarity is zero because dipole moment is a vector quantity and polarity due to one VEH is equal and opposite to the other. So net polarity is zero because of their linear arrangement. Question number 23 is related to NH3 and NF3. I will share the video, and I am already, I think, shared with you the video of comparison. It is very important question. It will definitely be in the exam. In your final exam, there are 90% chance that there is a question on this topic. Okay. Last topic, then we will cover hybridization concept only. Then our chapter is over, and we will do these exercise questions. Okay. Hydrogen bonding. So tell me, what is hydrogen bonding? Actually, hydrogen bonding, it is not like ionic bond or covalent bond. It is actually simple dipolar attraction. It is dipolar attraction between hydrogen atom and more electronegative atoms like fluorine, oxygen, nitrogen. We call it as phone, F-O-N, phone. When hydrogen interact with phone, that is called hydrogen bonding. So the atom attached to hydrogen should be small in size and is highly electronegative. This is the condition of the atom attached to hydrogen. Okay, and these two conditions are satisfied by fluorine, oxygen and nitrogen. I call it phone, F-O-N, P-H-O-N-E. Okay. So, actual definition of hydrogen bonding is, it is dipolar attraction. Like, see, if we have H and A, H is hydrogen and A is the atom which is small in size and highly electronegative. A is either fluorine, oxygen or nitrogen. So A gets partial negative and hydrogen gets partial positive. So this A will interact with hydrogen of other molecule or other group of the same molecule. Okay. So this type of interaction is called hydrogen bonding, and it is denoted by this shaded arrow, broken arrow. Okay, it is denoted by this type of notification. Okay, so this is definition of hydrogen bonding. Now types of hydrogen bonding. Types of hydrogen bonding. So first is hydrogen when attached to an atom which is small in size and is highly electronegative, then hydrogen gets partial positive and that atom which is more electronegative gets partial negative, and this partial negatively charged atom when attract the partially positively charged hydrogen of the other molecule or other group attached in the same molecule, then that type of bonding is called hydrogen bonding. This is one type of dipole-dipole attraction. This is dipole, this is also dipole. So these dipoles attract each other, but it is a special type of dipole-dipole attraction. Now, types of hydrogen bonding. I can write here types of hydrogen bonding, right? Yes, types of hydrogen bonding. So it is intermolecular hydrogen bonding and intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Okay. Now, according to intermolecular hydrogen bonding, in this case, hydrogen belongs to one molecule attract atom A belongs to other molecule. Like say inter-school competition between different schools, competition between different schools. Inter-college competition means between two colleges. Let's say intermolecular attraction, hydrogen bonding means hydrogen bonding between different molecules. So like in ammonia or HF, in HF, okay. So HF, it is like zigzag, okay. F likewise. So this type of hydrogen bonding is called intermolecular hydrogen bonding. F negative, HF, F negative, means one FH, then there is hydrogen bonding, complete, again hydrogen bonding, complete, hydrogen bonding, complete. Partially positive, partial negative, right? It is like this. Okay, so that is called intermolecular hydrogen bonding. Even in ammonia, N H. So H. Likewise, these are continue like this. So this is called intermolecular hydrogen bonding. Even in water, ice, there are intermolecular hydrogen bonding, like say in water. This is about ammonia. In water, in ice, O, H, H. There are two lone pairs and the two bond pairs, like this. Then this is hydrogen bonding in ice. Okay, so these are cages. Say there are different cages are formed. You know that when we melt ice, what happened? There are some cages. Those are the cages. So when ice melts, what happened? Water comes into these cages, so volume decreases. So volume of ice or density of ice, or we can say, if question is why ice floats on water, what do you write? Yes, tell me. This is the structure of ice, okay? Tell me, if question is why ice floats on water, what will you write? This is question of 8th standard. Why ice floats on water? Yes, because density of ice is less than that of water. And why density of ice is less? Because of the formation of these cages, and that is hydrogen bonding is responsible for that. So it is because of intermolecular hydrogen bonding. So in ice there are hexagonal, these are hexagonal cage like structures. So its volume is large and density is less than that of, because when ice melts, these cages are filled with water, so volume decreases, so density increases. Its volume is large and density is less than that of water. Okay, so ice, so density of ice is less, so ice floats on water. And how these cages are formed? Because of intermolecular hydrogen bonding. Yes, good beta. Next, intramolecular hydrogen bonding. So because of intermolecular hydrogen bonding, density increases, boiling point increases, okay? But intramolecular hydrogen bonding, so intra means when we have nitro and OH. See, hydrogen and atom, more electronegative atom, both are the part of the same molecule but in a different groups. Okay, so that inter-house competition means intra-school. So these two groups are attached to the same molecule. It is called orthonitrophenol. Structure you can remember now why it is known as orthonitrophenol. Okay, I will let you know when we start organic chemistry. Okay, so it is orthonitrophenol. In orthonitrophenol, there is a formation of hydrogen bonding between when hydrogen bonding is formed between hydrogen of one group and atom A of other group in the same molecule. That is called intramolecular hydrogen bonding. And because of intramolecular hydrogen bonding, boiling point decreases, it becomes inert, it cannot interact with other molecule, like in even this is called salicylic acid. This is salicylic acid. So in this case, the condition is that groups both are polar groups and groups should be at 1,2 position. Both are at 1,2 position. Okay, this is also called 2-hydroxy benzoic acid. So this is about hydrogen bonding, intermolecular and intramolecular. There is no need to remember the structure, but at least one you should know. Okay, because two polar groups on the same molecule, okay, they can interact to form intramolecular hydrogen bonding. To show it, we can remember at least one. Okay, so that's all for the day. Thank you.